Welcome everyone to this webinar on the capabilities with the AD2CP. My name is Jan Overly and I'm today's moderator. I'm joined by today's speaker, Chief Technology Officer, CEO and founder of Nortek, Atle Lorman. This presentation will last 25 minutes with questions taken at the end. Today's speaker is the founder of Nortek and has since 1989 been actively involved in the development of acoustic Doppler instrumentation for oceanographic applications. Atle holds several patents and continues to lead Nortek's development team. Today we're excited to bring you some highlights on the advanced 5-beam system Nortek is introducing this spring. So ladies and gentlemen, to talk about the capabilities of the new AD2CP, I give you Atle Lorman.
Thank you, Jan. Yeah, we're going to talk a little bit about the new generation of current profilers. We call it the AD2CP. The name is, of course, chosen for partially for its similarity to the traditional AD2CP, but we're also trying to emphasize that we're trying to do a little bit more this time. The two in this case really says something about the extension of this hardware generation compared to what we've been doing before. So the primary goal of this development was really increased flexibility. The hardware that sits in these types of instruments really determines what you can do with them, and it is very important that we try to find something that is as flexible as possible, because that really is what limits our ability to do the things that people would like to do or measure. So it's a multifunction system, and the idea is that we can have many combinations of beams, ping sequences, acoustic frequencies, and things like that. I'll get back to the details of some of this. It has proper broadband processing, something that's been kind of long awaiting. Smaller, lighter, lower power, and smarter interfaces. That's a big one today because the serial port is disappearing from the computers. So the traditional serial interface to these kinds of devices really doesn't work all that well anymore. It always had a lot of limitations, and serial ports really were there primarily for the purpose of having low power consumption. So coming up with new schemes there has been an important part of this AD2CP development. A secondary goal is really to develop a hardware and firmware structure that allows us to meet the requirements of the user community for a long time. We do realize that people want to do different things at different times, and as budgets, as capabilities, as prices, as ratings, and all that kind of thing changes, we would like to have something that allows us to flexibly and easily move from one application to another using the same hardware platform. So the whole structure of it really is intended to act in such a way that it's easy to modify and easy to do new things. So a little more details about this. In terms of the multifunction system, I think the key really is to try to implement systems that can do more than one thing at a time. Of course, it's kind of hard to define really what we mean by at the time, but in our world, sort of at the time really means within 1 second. So you basically allow the instrument to do different types of measurements within that 1 second, meaning that if, for instance, they can collect mean velocity profiles and high resolution data both within that 1 second time slot. Different data types. Traditionally, this has been water velocity types of devices. We're now looking at tracking velocities at different times, distances, something like that. There's really no limit. As long as it can be done acoustically, it can be done with this device. More than one frequency. We already have seen dedicated devices over the last few years that are basically operating on more than one frequency, and I think we already implemented something like that in the device that we call an AWAC a few years back, when we did something that combined 400 kilohertz and 600 kilohertz. But that was kind of, I wouldn't call it the kludge. It was a design that was very specific. In this particular case with AD2CP, we're trying to design something that inherently is capable of changing frequency from one transducer to another. And of course, as always, we're always thinking about more beams pointing in more directions. So traditionally, there's been 2, 3, 4, maybe sometimes 5 beams in these kinds of devices, but the typical maximum has been 4. In this particular case, the hardware design, again, is such that we can have more beams inherently hooked up to the same hardware platform. And the last one there is internal processing of data, which is important if you're going to do something that requires a lot of raw data collection and then some form of processing to reduce the data set. In order to be able to do that, you need to have some sort of processing capability inside the instrument, which really hasn't been there to a large or to any extent before. So that's also a new aspect of this multifunctionality. All of this is made possible by a two processor or two DSP design. One is dedicated to the broadband processing or to any other type of sort of core acoustic processing. And then today, the second one is mostly dedicated to interface processing, and we'll get back to the details of that. But basically, the idea that there is to allow us to share the burden of processing or of treating the data without having to interrupt the basic data collection schemes. DSP code written in C today. It used to be in assembly. For those of you who have ever written in assembly, I don't need to explain the advantages of that. And we did protect this whole thing. We actually took out a patent called the AD2CP. And really, it's a patent for doing many things at the same time. It's for those of you who are interested in the detail, you can look up the US patent. But it's sort of the concept of a multitasking device that has been patented in this one. So broadband processing, not going to go into the details. Of course, the hardware development of the AD2CP platform was timed to the international expiry of US patent 5,208,785. Looked at that a few times in my life. It expired internationally in September 2011. It's referred to as a broadband patent, and it is no longer a patent in the sense that it's no longer protected. So the schemes that are described in that patent are now free to use by anyone or everybody, which is kind of a good thing for the community in reality. There are different ways of implementing this broadband processing scheme. Nortek, or we chose one, which is a little different from the one that's out there typically today, where people are using face coding. In the case of the AD2CP platform, which actually we can implement different schemes, but the one that we're using for the devices we're talking about today are using frequency-based coding. And there's some reasons for that. It's not a lot better than face coding, but it's got some flexibility advantages that we like, and it is easier to define appropriate transmit sequences with this than it is with face coding. So we took advantage of that. The frequency-based coding sort of looks like this. It sort of changes basically frequency throughout the transmission sequence. You couldn't really do this 20 years ago, so it's the kind of transmit sequence you can produce today when you have DJ converters that are fast, and as you can sort of, this kind of sound that this makes when you transmit it sounds much like a bird chirping. So basically we refer to this as chirps. So this is the broadband processing scheme that is implemented in these systems. Lower noise and velocity data is the consequence of broadband processing, and it's not generally very important, but it is important in a few cases. And I think the ones that we are concerned about the most is long-range current profilers, vessel nanosystems, and turbulence measurements in high-energy environments. All of those three applications, there really are advantages of using broadband schemes. And so it's kind of natural that those three applications is also the focus of our effort when we're now talking about implementing the AD2CP hardware platform into specific devices. Smaller, lighter, lower power. Yeah, we all want to do that. Electronics advance. The components are getting smaller. Number of layers are increasing. PCB area in the new system is reduced by a factor of 2. Which is kind of impressive, considering that we actually reduced the AWACS and the Aquadot products by a factor of 2 back in 2010. So things are going fast. System is close to neutrally buoyant in water if there are no batteries. So that tight canister, it's a very light device. And power consumption in some of the applications, specifically the glider, has gotten all the way down to 200 milliwatts when sampling every 10 seconds. So today we're basically using the power that we're transmitting and nothing much more. It's really become a matter of how much or how far you want to profile, and that's what you pay in terms of batteries. The basic processing power requirements have become very, very small compared to where they were 10, 15 years ago. Smarter interfaces. Talked about the serial port. It's still there. We haven't thrown it out. we have actually expanded it to include today both an ASCII and binary serial interface. It took us a long time to understand that people really like the ASCII serial interface, and our sympathy with people who integrate with controllers or other devices have finally sort of gotten us to the point where we have a true ASCII interface to the device. So it's a lot easier to program if you're using an external controller. We also introduced a concept we call telemetry file, which is kind of a new thing. It really is about storing subset of the data for transfer over low bandwidth links. So if you're collecting lots and lots of data, you can imagine taking out a small subset, let's say every 10th sample, and put it into a separate file. That file can then be transferred over an Iridium link in case of gliders, or it can be transferred over an underwater acoustic modem in case of coastal instruments. Basically sort of a subset transfer system. And it works well and is very convenient for online applications like this. We also added an Ethernet port that's handled by the second DSP in the system. One important aspect of the Ethernet port, which is a hardwired thing, is that it's got a timing engine in there, a precision timing protocol, which allows us to set the time in the instruments within 10 microseconds. That's 7.5 millimeters in propagation distance for sound underwater. That is not something you can do with a PC. You actually need a precision device that has the same timing protocol, typically a GPS clock, to do this. But it allows you to take one or more devices and synchronize very, very tightly compared to what has been possible in the past. We also have an Ethernet discovery function in here, which means that you can find and connect to the instruments from your office. So if you have a bunch of instruments sitting in your lab, you hook everything up to a switch, you go back to your office, and you basically access all these devices from the pleasure of your office, basically. So it's kind of a nice thing for those of us that have cold storage areas. Linux operating system, there's TCP/IP protocol, web server in there. That's it's not a big thing right now, but it's in there. Important FTP server, that has improved the download rates radically compared to what we've been able to do in the past. So typical serial ports, 115K, maybe 600 kilobaud if you're doing over USB. With the FTP server using Ethernet, we have download rates of 20 megabit. So that means that a big file of 1 gigabyte can be transferred in 6 minutes. So a lot of the old concerns about transferring data over the wire and the need to open it up is sort of all gone. And you can hook up your Ethernet cable to your computer and get the data over very, very quickly compared to what was possible today. So in underwater applications, you can then imagine, and this has already been implemented in a couple of different projects, you can have multiple devices all connected over the Ethernet cable to an underwater switch. And the underwater switch can then be linked to a computer or a controller on the shore, where over a fiber optic cable or something like that. So the need to do sort of PC to one device type of structure, which you used to have in earlier, or we still have with some of the older devices here, that's gone in this new platform. So it's very, very, very suitable for large array type of applications. So the AD2CP products that have been implemented, basically the types of devices that we have implemented based on this hardware platform, started in 2012 with what we call the AD2CP glider. That was developed in conjunction with, or in collaboration with iRobot when they were working on the Sea Glider project. That sort of faded out in the background as iRobot canceled their whole maritime division. But Spray and the work that's being done at Scripps, and it was all sort of picked up on that a little bit. So we have, over the last year, helped install quite a few of these AD2CP glider systems on Spray gliders. So that's it's been quite successful, and it seems to be working well. There's also another one that really hasn't gotten much attention, something we've called an Aqua Lab 2. Long reasons for that, none of them very sensible. But this is the same thing. It's a single point device that is mounted on the McLean profilers. And it's been purchased by OOI. So these are the kinds of wire following profilers that go up and down. Super low power consumption, 200 milliwatts with 8 hertz output rate. But again, single point device, very specialized type of thing, not a commercial device. So we only sell this in conjunction with McLean. Signatue 55, long-range instrument. We're going to have a webinar about this in a couple of weeks. Not going to talk too much about it, but it's based upon the same hardware platform, the AD2CP. So today, specifically, the Signatue 500 and Signatue 1000 is a 1 megahertz and a 500 kilohertz device, 5 beams, and we'll talk a little bit about the details of this. And I'm going to start out with what we call the timing controller, or sort of what can you do with this? What does this device do that we haven't already been able to do? And I want to explain to you a little bit, and I don't want to get into too much detail about this, but the data collection scheme that we're using is basically a timing scheme where we fit for a given frequency a certain number of slots into 1 second, and that slot, or the size of these slots, or the number of the slots, is determined by how long it takes for the signal to fade out. So in a 1 megahertz system, we have 16 slots, which roughly corresponds to, well, what does that correspond to? It corresponds to about 40 meters, 30 meters. So each slot has got a fixed length, and within those slots, we can fit different types of operations or different types of ping sequences. And at this point, we're operating with 5 different ones. We have something we call a current profile along 4 beams, which is referred to as AP4. BP4 is burst profile along 4 beams. It's the same kind of thing, but it has a different outcome, so I'll explain to you later. BP5 is current profile along the vertical beam. Alt is altitude data, which is typically distance measurements like we have to the surface. So these kinds of ping sequences, if you wish, or measurement types can then be put into these different slots. The BP4 and BP5, basically the 4 beams are not being operated at the same time as the vertical beam. And that's kind of important to understand. And the reason is because the 5th beam is so close in angle to the other 4 beams that you would get cross interference potentially if you try to do them all at the same time. So not a good idea. It is conceivable you could do it, but the problem is that you can get small bias errors that you really don't want to have. And there's no way in post-processing to remove them. So we chose in the end to really multiplex the 4 slanted beams with the vertical beam to make sure that cross interference was not an issue. So if you just want to collect average data, typical example on the top here could be that you, in slot number 4, 6, 8, and 10, have a current profile ping going along all 4 beams. You take all that data and average together and output at the rate of maximum 1 hertz. Typically, you would output it much slower, like every 10 minutes. But those are the pings within that 1 second that will all be averaged together. You could also stick in a couple of other pings in there, an altitude ping, like towards the surface, or a bottom tracking ping. But it cannot output data at rates higher than 1 hertz, and usually much slower. A similar kind of thing is possible also with the 500 kilohertz, but this is sort of an average profiling mode, which would be your typical basic data collection scheme if you're only looking to have information about the mean current profile. The burst mode is, on the other hand, a mode that allows you to collect data very quickly. And again, there are different types of sequences you can put together, but in this case, you can store data at the sample rate. So if you look at the first option here, which is just BP4, it means ping with all 4 beams at 16 hertz and storing data potentially, if you want to, at 16 hertz. This is the mode that allows you to collect data very, very quickly. The second one option would be alternating between the 4 slanted beams and the vertical beam, so effectively giving you an 8 hertz rate for all 5 beams. So that would be, in the case of 1 megahertz, the maximum rate at which you could get data from all 4 beams. Then you could then start playing around with other things. In option 3, you're alternating between a current profiling burst and an altimeter. So all of these different types of options are possible to implement depending on what you want to do, so in burst mode. And then I think what's interesting about this, and this is 500 kilohertz examples, I just skipped this. It's kind of very similar scheme or similar thinking. You just sort of stick different types of measurements in at the different time slots you have available. You can combine this. So, for example, let's say there are 2 researchers trying to use the same device, and you have a 1 megahertz device. One person is only interested in the current profile, and the other one wants to look at turbulence. So the first person gets 1 minute data with 4 beams, data from 4 beams, and he has time slot 4, 6, 8, and 10, and basically measuring current profile along each one of those, each one of those slots. The data is being averaged together, and then typically there's a compass rotation coming in, so you're converting to velocity component, and then you take all that data and average over a 10-minute period, which is kind of a typical average current measurement interval. The other person wants to look at the turbulence, so he just fires off the vertical beam. So he has basically an 8 hertz data collected to a separate data file that he will get out of the same device. So he'll have 8 hertz data over a burst interval, whereas the other person will have just the average current profile along the slanted beams. So that's the way, sort of combining 2 different applications into one single device. And hopefully, basically the device can serve more purposes for different researchers in the same project. Again, examples for the same with 500 kilohertz, not going to go into details. This will be documented later on, so you can take a look at this in the details if you want to. It's coming into brochures and all that kind of thing. Very quick example. This is the 500 kilohertz deployment that was happening not too long ago in France, 25 meters of water. This was a burst mode, but it was a burst mode where data was stored at 1 hertz. You can still, even in burst mode, so you can basically store data at a different rate than you actually collect it. So here, your slot 1 is an altimeter, slot 2 is a vertical beam, 3 is slanted beams, 4 is vertical beam, and 5 is slanted beams again. So you basically alternated between the 3 modes, and it's all being stored, averaged and stored at 1 hertz. So you can see the device here is kind of this type of signature device with the 5 beams sitting at the bottom there. Example of the signal strength coming back. This is the amplitude of the data. Surface is around 25 meters. The green line here shows the strength of the return signal, with the surface being a big peak. You can take the upper part of this and fit to the sonar equation, which is the blue line. So you can sort of see that in the left-hand section of the plot, we've fitted the blue and green line together. The noise level is around 21, 22 count, or not counts, and actually dB in this particular case. We stopped putting out counts. This is to become a dB device at this point. So we can look at the noise level where it hits the noise floor. The sonar equation tells us then basically how long or what range this instrument would have given us if we had not had the surface there. So it's basically 1 meter resolution, 500 kilohertz, about 50 meter range, and that sort of makes sense. I think it's a good number. So in this case, you can look at the waves. This is the pressure sensor. So the time is along the horizontal axis, got the seconds there, and then typically, or not typically, you have about 1 meter significant wave height here. Waves going up and down. Very high resolution pressure sensor, but only collected at 1 hertz. Then we can add the altimeter data on top of that, which is right there. So now you can see the altimeter data, which is quite a larger excursion than the pressure sensor. And you can also then look at the vertical velocity collected with the vertical beam close to the surface. This is about 2 or 3 meters below the surface. The red line is, and I know this gets really busy, but the red line is out of phase with the pressure sensor and the AST, or the altimeter data, because the velocity and pressure is out of phase by 90 degrees. It's sort of a sine cosine thing. So this is all data then describing different aspects of the waves along the central axis of the instrument. Look at the spectrum of this. This is the wave spectrum as a pressure and the altimeter. The waves are centered around 6-7 seconds. Pressure sensor is incredibly high resolution in the AD2CP generation. I want to point that out because the noise level in the pressure sensor is only 1.8 millimeters at 1 hertz, and that's a 100-meter sensor. And that means that we do have the same resolution in this pressure sensor as we have in the parascientific sensor. So this is spectrum from the wave height. And then just a last slide here about the velocity spectra. And the blue top one here is the altimeter. The black one is the spectrum of the vertical beam velocity close to the surface. And the noise level of that is about 2.5 centimeters per second. So that's what you would have gotten. So basically where the spectrum flattens out is where it meets its noise level. And that noise level defines, in these cases, how well you can resolve turbulence. This particular site, there really was no strong currents. It was only 10-15 centimeters per second current. So there is no turbulence to be really looked at here. But the point is that this black spectrum in here sort of describes what you would have been able to see if there had been turbulence. So basically the turbulence level would have had to be above that black line if you were to really resolve it with this type of devices. And that's why this broadband thing comes in and why it's important with low noise devices. I also plotted in the green line here and the yellow line, which is the corresponding noise levels for the horizontal flow component and for the vertical component as calculated using sort of the traditional geometry algebra with the 4 beams. So the black one is sort of a pure 1 beam vertical estimate of velocity. So Signature 1000, Signature 500. Introduction. We've been working on this for a long time. It is ready. It's been a lot of testing. It's being introduced at the Ocean Sciences Conference in Hawaii and towards the end of the month. Shallow water design. This is a 300-meter design. It's based upon AD2CP hardware. We've got 5 beams with a center beam multiplex. And I'd like to emphasize that this really is a device designed for scientific applications. There is no real software for processing waves or for processing turbulence or anything like that. This is a device that collects loads of data. It generates MATLAB files. It's great for turbulence measurements in high energy areas and sort of for studies of different kinds. So the way we think about it anyway is that we designed it and we present it to you as a scientific study tool. Thank you very much.
Okay, thank you very much, Atle. That was very interesting. As we talked about earlier, we are now open for questions. Alex Souza, are you with us?
Can you hear me now?
Yes.
Hello?
We are here, Alex.
Okay. Like roughly what's the single ping noise that you expect, or what's the kind of level of noise you will expect in turbulence at 8 hertz, for example?
So I can go back and show you the screen that we just had on here. The black one here. This is, as I said, this is a 500 kilohertz device, and it's got 1 meter resolution. And the black spectrum there is the average of 2 pings, and it has a velocity ambiguity of about 2 meters per second, and the noise level is 2.3 centimeters per second.
Okay, and how with the one kilohertz, what's kind of velocity amplitudes can you be measuring at frequencies?
The velocity amplitude is programmable. So in the configuration software, you have a parameter that we call ambiguity velocity, which is the highest velocity that you can unambiguously resolve, and that's the programmable parameter. Typically, the noise level will go up as you increase the ambiguity velocity. So, but there really is no limit. I think you can go up to 5 meters per second in the vertical velocity if you wish to do so. But it has consequences for the noise level.
Does the solving in frequency makes it easier to deal with ambiguity velocities?
Yeah, I mean, the big thing about the 1 megahertz device is that you can ping a lot faster, right? So you can also average more data together, which will reduce the noise.
Yes. Okay, thanks.
You're welcome.
Thank you, Alex. Okay, we have one more question coming in from Kevin Oberg.
Okay, can you hear us?
Yes, we're here.
Okay, Corey, we have a little bit of an audience in here. Corey, go ahead.
Yeah, we're just wondering what the vertical resolution or the bin size of the 1 megahertz system is.
The minimum one, I think we run it up to 20 centimeters.
Minimum. Same for the 500?
Well, I mean, the data that I collected there was 1 meter. In principle, you can go down to half a meter. But of course, I mean, the penalty, of course, is the noise level goes up. You're welcome.
Thank you very much. Okay, no more questions? Okay, it seems, well, Thomas, are you here? Thomas Virguts?
Yes, I'm here. Can you hear me?
Yes, we can hear you.
Okay, hi. What was very interesting to see about the new capability of the instrument. So I have a question regarding renewable energy. Would it be possible to get turbulences behind and in front of these water turbines?
Well, I mean, that's really not a. I suppose it's not really an instrumentation question as much as it is really sort of a physical question. But I mean, there is a lot of work that has been done, obviously, with in the tidal turbine industry, or just the tidal energy industry, with these kinds of devices. And I think that you sort of have to look at this as an information gathering system, and then the question really is sort of, is the information that you get from this adequate for the purposes that you are looking for, or for the types of questions that we are looking for. And the advantage that I see with the vertical beam is that you isolate one velocity component instead of having to look at basically what's going on along each beam, because the problem with the beams is that they're coupling different velocity components, right? I mean, any beam is sort of a coupling between the UV and W, or at least U and W components. So you can't really sort of isolate out the different terms in the turbulence equations when you're slanting the beam. So, I mean, there's an old trick that we used to do in the old days, right? Where you take basically the variance, you square each of the velocities along the beams, and you end up with these products, combination products between U and W, so like U prime, W prime, and you get the U prime squared and the W prime squared, and all those parameters that basically belong in the turbulence studies. And the vertical beam allows you a fifth equation that resolves W prime squared all by itself, and that allows you to resolve the whole sets of equations. So if you're looking to estimate the turbulent kinetic energy, for instance, before and after your turbine, this device will allow you to do that, assuming that the scales are not totally out of whack. So if the device has to be large enough in scale that the beams are basically measuring in areas that are statistically similar. I don't know if this got a little complicated, but it's basically. It's not a super simple question, but I would say that as long as the device as long as the information you're looking for is on a reasonably large scale, the answer is yes. If it isn't, then you would have to contend yourself with basically the vertical component only of the turbulence at a more specific size, because then you're down to a sampling volume that's basically only 1 meter tall and has the diameter of the acoustic beam.
Okay, thank you very much.
Okay, thank you, Thomas. We also have a couple of questions coming in from the questions from the audience window. From Nika Winders, he says, let's say we install 1 megahertz on a glider. What type of range can we expect from the different type of measurements, assuming the glider goes 1 or 2 knots? Hadley.
Well, the glider device actually is the 1 megahertz device, and the range we've been getting, obviously, it changes with where you are in the water column. Close to the surface, there's more stuff, and the range typically will be longer than it is close to the bottom. And my impression from the data that I've seen from Scripps, which is sort of going out in and out along the California coastline, not perpendicular basically to the coastline. My sort of rough estimate is 20 meter plus in the surface area, which will be maybe the upper 50 to 100 meters, and then it can go down to, I would say, 10, 12 meters as you get down to the clear layers below sort of the surface layer. But it doesn't seem to go down much below that, and it's never really sort of stopped working.
Okay. That was a good question, Vindos. We also have Dana, who has raised her hand. You will be unmuted, and if you activate your audio, we may hear you. Dana Savage.
Yes, I just wondered if you had a brochure developed or some literature you could provide our links to for questions like beam angle and whatnot.
Right. Well, the beams are 25 degrees, just to clear up that one right away. No, we haven't. we've sort of been busy doing the development and testing it and things like that. The brochure is going to be ready for the Ocean Sciences Conference, which is the official release of all this. So no, there really aren't any links yet. The presentation we've done today is really the only thing that's out there so far.
Okay, well, if you can send those out when you are ready to release them, that'd be great. And I just wondered if they have a target price.
My apologies. What was the last one?
A target price, just order magnitude.
Yeah, 2025.
Great, thanks.
Okay, thank you so much, Dana. We have a couple of more questions, so we will hold on for all of you who have questions. We have one from Brian Apology. Are there any trial developments planned in high energy current environments, Sally?
There are actually two. One is going on right now, which is in the British Channel. It's on the French side, and it's a tidal energy project, and they're putting out a 500 kilohertz or Signatue 500 in, I think it's about 40 meters of water, and it's going to be out for about a month, and they're collecting a humongous amount of data. I think they're expecting between 2 and 3 gigabytes. So that's the first one. The second one is the test project. That the first one is actually a commercial project, so it's a kind of a real thing. The second one is a test project that we talked about doing in Ireland, where we are going to put out a 1 megahertz system in an area with very, very large waves. So it's kind of a test of both sort of the combination of wave measurements and high energy in terms of the current flow.
Okay, Brian, I hope that answers your question. We have also one from Christoph Kluber. Okay, he asks, is it possible to get beam velocities as output?
Actually, today it's not even an option. As the last system we've been testing, actually it does give beam velocities. So all burst velocities are going to be output as beam velocities.
Okay, that answers your question there, Christoph. Any more questions? Seems that we have none. Yeah. Well, I think that wraps everything up. We thank you so much for joining this webinar, and we hope this was a valuable insight into the capabilities of the AD2CP coming this spring. We will be continuing on Nortek Speaker Series next week, and we hope to see you on the forthcoming Tuesday on the 11th of February when Peter Rosello talks about operation of the Victorino Profiler. We hope also that you will take the time to answer our short survey, which will pop up at the end of this presentation, and again also in a follow-up email we will be sending out. So this is Atle and Jan in Oslo signing off. Thank you for joining us.
Thank you.